Thanks. Hi, everyone. Thanks for the introduction. I'm Eric Hayden Campbell, and I'm going to tell you again about relational automated verification. So if we were to try and describe some holy grail of verification research, what do you think it would be? That's a rhetorical question. I would say that it's to decide all properties of all programs. This is obviously just as fictional as the Arthurian Holy Grail, which we've known sort of since almost the beginning of computer science as we know it. Turing's 1936 result of the halting problem is undecidable, and then the much more depressing result from 1951 that says that all non-trivial semantic properties of Turing machines, general purpose programs, are undecidable. So are we screwed, right? Why, how do we make progress in this domain of trying to prove properties about programs when we know that anything interesting is impossible? The way that we do this is sort of by trying to get as close as possible, for whatever that means, to general purpose verification while still maintaining decidability. On the flip side, we can just try our best to decide properties that we know are undecidable. And the way that we start this endeavor is by writing down the properties that we want to decide and the programs that we want to decide things about in a program logic. And this will let us reason symbolically about the kinds of programs and properties that we want to prove. Then we come up with decision procedures that check these properties. And there's a kind of complicated element of almost co-design or an interface between these two where we sort of carve out pieces of logics that we know are decidable, or sort of try and expand our decision procedures to cover more aspects of logical fragments. The final piece of sort of verification research is making these things practical and usable by programmers. And of course, this sort of plays tightly with the kinds of program logics we decide. We define the shape that they play, as well as what kinds of properties we care about deciding and what kinds of things we care about deciding. Okay, so let's get into the papers and how they relate into this framework. The first paper is an algebra of alignment for relational verification by folks from Yale and Stevens Institute of Technology. And this kind of fits into the program logic section. So let me tell you about, okay, let's back up, talk about verification. We tend to think about things in terms of core logic, where we reason about, we symbolically prove that all states that satisfy the precondition when run through the program satisfy this postcondition. In relational Hoare logic, we reason about pairs of programs. And so our preconditions describe relations on input states to these pairs. And the postcondition, again, describes relations on output states. And so the trick to doing these verification queries and writing these proofs is finding good alignments. Okay, what's an alignment? The best way to show this is by example. So let's say I have this program on the left, which initializes I to 5, R to 0, and then decrements I until R is 5. We might want to prove this equivalent to this program on the right, which initializes I to 10, and then decrements by 2. So we could try and prove something monolithic about these two programs, for instance, that they both result in R is equal to 5, or we could try and reason about them together. And that's what an alignment does. An alignment says, hey, these I's are serving similar purposes, so we want to think about them together. The R's are also, we want to think about the R's together, and we want to run these loops in lockstep and reason about their behavior at the same time, because sort of the other parts are less relevant. So how does this really work? So we describe an alignment as a pair of programs, and we do our sort of verification tasks and write our proofs compositionally. So we might start with T, which is just true, and then after running this first command in parallel, we see that I on the left is half of I on the right. Twice I on the right, sorry. Oh, I got that backwards. The R's are equivalent to each other, and then when we run through the loop, we can sort of see into the verification that says that R's are equivalent at the end. The way that the authors do this is they rely on classic machinery developed by Stephen Cole-Cleany and Dexter Cozen called Cleany algebra with tests. Their logic, however, allows you to reason about two pairs of programs. It's called BiCAT. And they have some cool results that they can rederive the axioms of relational Hoare logic and do some cool meta theory about for all properties and for all exists properties. Okay, paper 1. Paper 2 is called HFLZ validity checking for automated program verification. What is HFLZ? Let's just start there. HFLZ is a logic equipped with a least fixed point operator, a greatest fixed point operator, simply typed lambda abstraction, and integer predicates. Okay, this fits into decision procedures, but like, no, we're not going to be able to actually, we're not going to be able to actually decide these because the logic is far too powerful. So what are we going to do instead? We're going to build, or the authors are going to build, a HFLZ validity checker. By reduction to new HFLZ, which is another undecidable logic that they have built an efficient checker for. So the way that this works is you take an HFLZ formula and you do an under approximation of the least fixed point operators. Forgot to say this. New HFLZ does not have least fixed point operators. It only has the greatest fixed point operator. So you under approximate the least fixed point operator by basically finitely unrolling the loops, recursion, function calls. And then you pass that to the validity checker, and if you get valid, because it's an under approximation, you know that your original formula was also valid. If it's invalid, you can't conclude anything, and so you just continue, you just increase n and keep going until you either prove validity or run out of patience. The trick is in under approximating higher order functions. And the way that the authors do this is they instrument each function call, each abstract function f with some lower bound information about the way that the function is unrolled. More details in the talk and in the paper. Okay. The third talk, which is actually the second talk in order, is Grisette, which is symbolic compilation as a functional programming library from folks at Washington and Google Research. So what is symbolic compilation? The idea behind symbolic compilation is that you take a general purpose piece of Haskell code on the left, and you compute a symbolic representation of all possible execution paths. Now, okay, all possible execution paths is a scary word because there are way too many of them. And this is called the path explosion problem. And one way that the authors tackled this problem is using an ordered guards representation, where rather than enforcing that the conditions for each of these conditionals are mutually exclusive by negating the previous predicate, they use a syntactic rather than symbolic, a syntactic mechanism that sort of enforces an order for the guards and enforces them to be mutually exclusive syntactically. And this allows them to do more efficient path merging by just producing smaller predicates. It also allows them to do some classic VC optimizations and get performance speedups using memoization. The last piece is that Grisette is also a Haskell library for a fully functional language. It has an ergonomic monadic design, which makes it very easy to use. It's a very nice example of a Sigus loop in the paper that's very clean. And they use type classes to allow symbolic reasoning about built-in Haskell data types, which is really cool. That's not something that Rosette or some T-solvers or sort of any existing work has allowed you to do, which is, I think, one of the biggest contributions of the paper. I'm over time, so thank you.